Welcome to the third part of Lesson 1. In this section, we are going to review how acids and bases work. Specifically, we will review the Bronsted-Lowry theory of acids and bases applied to organic chemistry. In this section of the lesson, we will review the concept of proton transfers, acid-base equilibria, and learn how to predict, quantitatively, the outcome of acid-base reactions. You might recall that acids and bases have been described in various different ways in the history of chemistry. One of the most useful descriptions of acids and bases is called the Bronsted-Lowry definition. In the Bronsted-Lowry theory, all reactions between acids and bases involve the transfer of a positively charged hydrogen atom, which is also just called a proton. So in the Bronsted-Lowry theory, a proton, which is just an H+ ion, can move between two chemical species, a proton donor and a proton acceptor. In the Bronsted-Lowry theory, the proton donor is called an acid, and the proton acceptor is called a base. Now that we have the definition of a Bronsted acid and base, we can look at many chemical reactions, such as the example shown below, and classify the chemical species as acids or bases, based on whether that species is either accepting or donating a proton. In this example, we can see that the species HCl has a hydrogen atom, shown in red. It is possible that this proton could be transferred to a different chemical species, such as the water molecule that we see shown next to the HCl molecule. Transferring the proton, that is to say, the hydrogen atom without the electrons that were in the covalent bond, to the water molecule, is a Bronsted-Lowry acid-base reaction. The acid is the HCl molecule, the proton donor. The base is the water molecule, the proton acceptor. Notice that when the proton is exchanged, the charges of the chemical species are changed as well, as is shown on the product side. The charge of the chlorine atom decreases by 1 unit to -1. This makes sense, because the chlorine lost a positively charged hydrogen atom. The charge of the water molecule increased by 1 unit, because it gained a positively charged hydrogen atom. So if the proton donor is called an acid, and the proton acceptor is called a base, how do we describe the chemical species on the product side? Let's go to the next page and find out. A good analogy for the Bronsted-Lowry concept of acids and bases, and proton exchange reactions in general, is a game of catch between two people. If we think about a game of catch, we have two roles for the players in the beginning. The person with the ball, which we can imagine represents a proton, is the acid. When this person throws the ball, or proton, they are acting as a proton donor, the acid, and the other person, the one who catches the proton, is the base. But notice that after the ball is caught, the two roles are now reversed. The person who caught the ball acted as the base initially, but now they are the person that can act as the acid, because they have the proton ball to donate. So after the ball is thrown, the roles of thrower and catcher are reversed. Similarly, in an acid-base reaction, the roles of the acid and base are switched after the proton is exchanged. So that we don't get confused, we introduce the terms conjugate acid and conjugate base to refer to the new roles that are assigned to the products that are written on the right-hand side of this exchange. So, on the left-hand side, we have the acid and base. But then on the right-hand side, we use the terms conjugate acid and conjugate base. If we look at the example shown below, we can classify all of the species in the acid-base reaction using this concept. We start by comparing the left-hand side of the reaction with the right-hand side, and we locate the proton being exchanged. Once we identify the species that is donating the proton, on the left-hand side of the reaction, we classify that as the acid. In this case, it is the water molecule. The other molecule, which is called tert butoxide, is the molecule acting as the base, because we can see that it converts into the product that has gained the proton. Now that we have our acid and base assigned, we can find the conjugate acid and conjugate base on the right-hand side of the reaction. Looking closely, we can see that the proton, shown in red, is on the oxygen atom of the molecule that we called tert butoxide. Now that it has the proton, it has a different name. It is called tert butanol. Tert butanol is the conjugate acid, because it can now donate the proton. We also see that the water, having donated a proton, has converted into a hydroxide molecule, which has one less proton than water. Hydroxide is the conjugate base of water. Tert butanol is the conjugate acid of tert butoxide. Now, let's look at this entire chemical reaction as a whole. We can see that the reaction is reversible, that is to say, it can run in two different directions. The reaction can proceed from left to right, starting from the acid on the left, and going towards the conjugate acid on the right. Alternatively, the reaction can also run from right to left. In this case, the reaction would start from the conjugate acid, and go towards the acid. This is what actually happens in reality. Proton exchange reactions like this are constantly shifting backwards and forwards. Ultimately, they establish a balance where the concentrations of the acid, base, conjugate acid, and conjugate base are constant. This state, where the concentrations are constant, is called equilibrium. The position of this equilibrium, meaning the side of the reaction that is favored with a higher concentration, depends upon the strength of the acid compared with the strength of the conjugate acid. Whichever acid is weaker, that is the side that the equilibrium will favor. If we know the strengths of various acids, we can predict the outcome of most acid-base reactions, simply by comparison. This is incredibly useful because proton transfer reactions are the most common reactions in chemistry. Being able to predict these reactions is essential. Let's go to the next page and learn how to do this comparison, and try a few examples. When we try to predict which side of an acid-base equilibrium will be favored, we compare the relative strengths of the two different acids, that is, the acid on the reactant side, and the conjugate acid, the acid on the product side. Using our analogy, if we think about two people throwing a ball back and forth, if they both throw and catch exactly the same, then there would be a 50-50 balance in the equilibrium. On the other hand, if one of the people was much better at throwing the ball, we would say that person was the stronger thrower. The ball would spend most of its time with the other person. We can think of acid strength in the same way as the strength of the thrower. To determine which side of the equilibrium is favored, we would need to compare the strengths of the two different acids on either side of the reaction. The side with the weaker acid would be the one favored at equilibrium, because the proton, just like the ball, would be favored on that side of the reaction. In chemistry, one way we compare the relative strengths of two different acids is by comparing their acid dissociation constants. This constant, Ka, is the equilibrium constant for the dissociation of an acid into its conjugate base and a hydrogen ion. Mathematically, it is defined as the ratio of the concentrations of the dissociated ions to the concentration of the undissociated acid when the system reaches equilibrium. Ka is directly proportional to acid strength. As Ka increases, the strength of the acid also increases. Conversely, as Ka decreases, the strength of the acid also decreases. A Ka value greater than 1 indicates that the acid is strong. This means that the acid dissociates to a significant extent in solution, producing a relatively high concentration of hydrogen ions. In other words, at equilibrium, there is a higher concentration of dissociated ions compared to the undissociated acid. A Ka value less than 1 indicates that the acid is weak. Weak acids only partially dissociate in solution, meaning that at equilibrium, there is a higher concentration of undissociated acid compared to dissociated ions. In the case of weak acids, the equilibrium lies more towards the side of the undissociated acid. This means that only a small fraction of the acid molecules dissociate in solution. While Ka values are not inherently inconvenient, they can present some challenges, especially when comparing acids with vastly different strengths. Specifically, Ka values can span several orders of magnitude, ranging from very small values for weak acids to very large values for strong acids. Dealing with such a wide range of numbers can be cumbersome, and may require logarithmic scales for practical comparison. For this reason, and others, chemists frequently use a related but different value for describing the strengths of acids. This value is called pKa, and it is calculated by taking the negative logarithm for an acid's Ka. By doing this, the pKa values for most organic acids fall between the much more convenient range of -10 to +50. One important point to remember is that pKa values are inversely proportional to acid strength. As pKa values decrease, the strength of the acid increases. For example, hydrochloric acid, which is a strong acid, has a pKa value around -6. Acetic acid, on the other hand, a weaker acid, has a pKa close to 5. Water, which is a very weak acid, has a pKa of 15.7. Notice as the values increase, acidity decreases. Another benefit of using pKa values is that we can easily compare the acidity of different functional groups, making it a simple matter to determine when one type of molecule will be able to donate or accept a proton from another. Let's look at that on the next few slides to see some examples. As is shown here, the pKa values for most organic molecules is easily determined by looking these values up in tables, and also knowing the approximate pKa values for common functional groups. In these tables, the pKa value refers to the most acidic proton on the molecule, unless indicated otherwise. To avoid needing to remember a huge number of slightly different values, it is convenient to cluster molecules in groups of 5 pKa units. This is called a simplified pKa table. And an example of one that we will use is shown on the next page. Here, we can see a depiction of a simplified pKa table, which has rows that span 5 pKa units. In each row, we see common functional groups that have pKa values that fall within these ranges. For each functional group, the specific proton that the pKa value is based on is highlighted in red. This version of the pKa table, which spans several pages, is available for you on the course website. With an understanding of how pKa values correspond to the strength of an acid, we can now see how they are used to predict the outcome of acid-base reactions. Simply put, if two chemical species are exchanging protons, the proton will always prefer to stay with the weaker acid. Borrowing from our earlier analogy, stronger acids are better at throwing, and weaker acids are better at catching. To see how this works, let's consider the proton transfer reaction between water and tert butoxide again. To determine which side the equilibrium will favor, we need to compare the strengths of the acids on both sides of the equilibrium. We see that the acid on the left-hand side is the water molecule, which has a pKa of 15.7. The acid on the right-hand side of the equation, the conjugate acid, is tert butanol. Tert butanol has a pKa of 18. Which one of these species, the acid or the conjugate, is the stronger acid? That's right. Water is the slightly stronger acid, as it has a pKa about 3 units below that of tert butanol. Because water is the stronger of the two acids, water is better at donating the proton than tert butanol. As a result, the equilibrium will favor the right-hand side of the equation, where tert butanol has the proton. Using our earlier analogy again, tert butanol is better at catching, whereas water is better at throwing. In all acid-base equilibria, the reaction will always favor the formation of the weaker acid. We just need to identify the acid and the conjugate acid. Once we have identified the two acids, we compare their pKa values. The equilibrium will always favor the side with the acid having the higher pKa value, as that is the side with the weaker acid. To summarize again, if two chemical species are exchanging protons, the proton will always prefer to stay with the weaker acid. As another example, let's determine if the compound N-butyl lithium is a strong enough base to deprotonate water. First, we need to complete the reaction equation by drawing the conjugate acid and conjugate base. Since we are told that N-butyl lithium is acting as the base, that means water is acting as the acid. The conjugate base, therefore, would be the water molecule, but with a hydrogen ion removed, leaving only the oxygen connected to one hydrogen atom. The oxygen would have 3 non-bonding electron pairs and a negative formal charge. This is the hydroxide ion. The lithium cation is present, forming an ionic bond with the hydroxide ion. It is a spectator ion, as it has not changed during the course of the reaction, and therefore we can ignore it. The conjugate acid is simply the base, with one extra hydrogen ion attached with a covalent bond. This gives the terminal carbon atom 4 total bonds and no lone pair electrons. This molecule is now neutral and is called butane. Now that we have drawn the products for the acid-base reaction, we need to label the acid and conjugate acid with their approximate pKa values. If we look in our table, we find water at approximately 15. Where do we find the conjugate acid, butane? We need to identify the functional group in butane. We have a hydrocarbon with all single bonds. As we discussed in the introduction to functional groups, this is called an alkane. In our simplified pKa table, we see that alkanes have a pKa of approximately 50. Looking at the acid-base reaction, can we predict if N-butyl lithium is a strong enough base to deprotonate water? Yes, we can. We see that the conjugate acid, butane, has a pKa of 50. This means that butane is a significantly weaker acid than water, which has a much lower pKa of 15. Water is a much better proton donor than butane, and so we would expect butane to keep the proton. So yes, N-butyl lithium is definitely a strong enough base to take the proton from water, because it converts into the much weaker acid, butane. Now that we have seen how this process works together, I want you to try a few on your own. Let's go to the next page and have a look at the first of these examples. In this example, your task is to determine if the acetate ion, shown below, is a strong enough base to deprotonate the ammonia molecule. A complete solution will include the following. 1. A completed reaction equation with the structures of the conjugate acid and conjugate base. 2. The approximate pKa values for the acid and conjugate acid. 3. A circle around the species that will be favored at equilibrium. And finally, 4. A yes or no answer to the question of if acetate is a strong enough base to deprotonate ammonia. Pause the video so you can work on this problem, and when you unpause the video, we will discuss the solution. Here are the structures of the conjugate acid and conjugate base. The conjugate acid has the functional group, called a carboxylic acid, which has a pKa of approximately 5. The acid in this reaction is the ammonia molecule. Ammonia is in the same category as amines, which have a pKa of approximately 35. Given these pKa values, we can see that the ammonia molecule is a much weaker acid than the carboxylic acid, and so the equilibrium will strongly favor the left-hand side of the reaction as it is written. This means that acetate is not a strong enough base to significantly deprotonate ammonia. In this next example, your task is to determine if the hydroxide ion, shown below, is a strong enough base to deprotonate the alkyne proton on the molecule shown below. Please pause the video so you can work on this problem, and when you unpause the video, we will discuss the solution. Here are the structures of the conjugate acid and conjugate base. The conjugate acid here is just a water molecule, which has a pKa of approximately 15. The acid in this reaction is the alkyne. Alkenes have a pKa of 25. Given these pKa values, we can see that the alkyne molecule is a much weaker acid than the water, and so the equilibrium will strongly favor the left-hand side of the reaction as it is written. This means that hydroxide is not a strong enough base to significantly deprotonate an alkyne. This concludes Lesson 1. Congratulations! Before moving on to the next lesson, you will need to make sure you practice and reinforce the topics we have just reviewed. For example, be sure to complete any outstanding tasks, such as homework assignments, quizzes, and readings that you are assigned. These tasks will help you practice and strengthen your recall on these fundamental topics, so that you can use them with ease in the next lesson. As always, please ask for help when you have questions. See you in the next lesson.